get into other stuff later. But this this is 5.6. So some guidelines for solving them, and I don't necessarily follow every single one of these every single time. It kind of depends on the question, but identify all given quantities and quantities that need to be found. Make a sketch and label the quantities. So in a lot of cases, I am going to be drawing something, but it might not be like, depending on what it is. It might be like, oh, I'm drawing a triangle or whatever. It might just be drawing a little shape or something to like get you from point A to point B kind of thing. Write an equation involving the variables whose rates of change either are given or are to be determined. And a lot of times those are going to come from your derivatives. And then use the chain rule and implicitly differentiate both sides of the equation with respect to t. And then after step 3, substitute into the resulting equation all known values and solve for the required rate of change. So that one, like, again, it just depends on what they're asking us for. Sometimes we're like really plugging something back in. Sometimes we're literally just solving for the missing pieces. So this first one. Police cruiser is approaching a right-angled intersection from the north, is chasing a speeding car that has turned the corner and is now moving straight east. What in the world is happening? It's supposed to say cruiser, is 0.6 miles north of the intersection and the car is 0.8 miles to the east. The police determined with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So, just to kind of get like a visual here, I have the intersection, and the police car is coming from the north. So I'm going to just draw a little arrow here. I'm going to basically make a triangle. So this is the cruiser. And then to the east is the speeding car going this way. And they told me it's a right-angled intersection. And so then I'm thinking in my brain, okay, I'm probably going to be seeing a triangle here, so I'm going to go ahead and put that other side on there. Not that obviously, you can just drive through the middle of something, but for the sense of the problem, we pretend that I can. So I'm going to call east X, like the north-south direction Y, and then the other direction is Z. You'll notice these are going to be the common letters with that. I mean, you can use A, B, C, and D, or A, B, and C, whatever for the Pythagorean theorem and stuff that you end up using. But anyways. So then I'm going to take and I'm going to put down things that I know. So every basically variable that we're given, we're going to have the variable and then we're going to have its derivative with respect to t. So that's why we know that we're implicitly differentiating. So I'm going to set up x, y, and z, and then I'm going to have dx dt, dy dt, and dz dt. And I may do some of these and I end up not needing them at all. Some of the stuff might be irrelevant information. At times you'll see me end up just crossing something out because I'm like, we don't need this. So like we can just kind of ignore it. Not that it's bad to have, but So anytime I see a right triangle, my mind immediately goes to, Pythagorean theorem. So I like to go ahead and kind of like write that down. So x squared plus y squared equals z squared. So that's all stuff that I have, whatever. So now I'm going to take this and I'm going to write all the information in that I'm given in the problem over here into my little table of things. Like I said, may or may not need everything, but we're going to put it down as if we do. So, it says that when the cruiser is 0.6 miles north of the intersection, so that means that y is going to be 0.6. And I'm going to put units on that because obviously final answers are going to need units. That way I can check them. And then it says the other car is 0.8 miles to the east, so that's going to be x. And then the distance between them and the car is increasing at 20 miles per hour. So that's going to actually be this Z value here of the distance. So even though they can't like necessarily drive through the middle, the rate like between them essentially is like the saying as the crow flies of what's that rate increasing at. And so that is 20 miles per hour, which is my dz dt. So then it says, if the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So that means dy dt is 60 miles per hour. And let's see, they're technically from the north traveling south, so that means that this would be a negative 60. So kind of like in physics, like directions are going to give us positives and negatives as well. So I'm solving for dx dt. So a lot of times initially, especially if you have like a pencil or something, I'll put a question mark where the thing is that I'm solving for. If it's just one thing, I may go ahead and put like a little circle around it and then I'll just fill it in, whatever. Now, obviously I can look at this formula and know, okay, well, I'm probably going to need Z. They didn't give me Z, but do I have enough information to find Z? Yeah. So I can use the Pythagorean theorem to find Z, and so that's just 0.8 squared plus 0.6 squared, and if I take the square root of all that, that's going to be equal to Z. So we've got, that's nice. So Z ends up actually being equal to 1. Oh, that should make sense. 0.64 and 0.36 add up to 1. So 1 mile then is the distance like between them as the crow flies. Okay, so now I need to find the speed of the car. So that means I'm solving for the derivative that deals with the car. So I'm going to implicitly differentiate all of this. So this will be a little refresher of doing that. So we put the 2 in front, so we have 2x. And then normally this is where when we were doing it like y with respect to x, it would have been like y prime. Yeah. But we're going to write dx dt because obviously we have a bunch of variables, and what we're taking the derivative with respect to, like t isn't even in our equation. So this will be dx dt plus 2y dy dt is equal to 2z dz dt. So at this point, you can either go ahead and plug stuff in. I usually like to solve for whatever I'm like trying to get by itself first. But that's just the way that Mr. Cass ingrained it in us, was that you should always solve your equation first and then plug everything in. But it's really up to you. It's not like right or wrong one way or the other. So I'm going to subtract this 2y dy dt, and then I'm going to divide by 2x. So dx dt is equal to 2z dz dt minus 2y dy dt all over 2x. Now, at this point, if you want to, since all the pieces have a 2 in them, we can go ahead and get rid of that, because that would be like factoring it out. Just remember, when you do that, it has to be in all the pieces of like the top if it's being added or whatever. So then dx dt is equal to 1 times 20 minus 0.6 times negative 60 all over 0.8. And that gives me 70, and then that'll be miles per hour. So then I usually will come over here and I'll erase my little question mark. And a lot of times I write it in a different color, but you don't have to do that. I just, since I'm, on here. And then I'll just circle what the thing is that I was trying to find. I mean, if you have all the pieces there and you set it up like this, like if you forget to circle it, I'm going to be able to figure out what you were solving for, even if nothing else, to go back to your work and see that like you knew what it was. But so anyways, so that's the first one. So not too bad, but obviously they're really not that difficult. It's just like you're going to find it's going to be really looking at what am I solving for, what pieces do I have, and sometimes it's like, okay, I'm not given all the information, can I find the other information using something that I know? So the second one here, a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. So that just basically means that they're just continuously going out. Like if you had, you've probably seen it before. You've probably thrown a rock in the water and seen that. I don't know if the little thing behind your house is like moving water or not, but so you can probably see it at home. But anyways, the radius of the outer ripple is increasing at a constant rate of 2 feet per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. The other thing is obviously watch units. Normally they're pretty good at giving you everything in the units that are needed and not like, ones in inches, ones in feet. But occasionally that does happen, so just make sure you pay attention for that as well. So I'm looking at area, and so basically I know that I'm going to just draw a circle here, but this is one where I don't always draw a picture, but come in.
Hey.
Hi.
Question for you. Do you have, sorry to bother you.
No, you're good.
One of like these workbooks for our Algebra 1 book? I started using this one, but then it doesn't line up for all of the lessons.
Yes, there's one that says like current book on it, and I do have that one.
Awesome.
I have to figure out where I stuck
Don't
it.
try that. Like I've been like scrounging worksheets like just online and stuff, but if you have one, that'd be awesome.
Yeah, this one should be our current book.
Awesome. You're the best. I will
Yep.
make copies. Thank you so much.
No problem.
Thank you.
No, you're good. Thought it was gonna be Anthony.
Yeah, me too.
So I was like, who's at the door? Okay, so anyway, so I'm dealing with area of a circle, so I know that really the only variables are area and then radius, so A and R, and then I've got dA dt and dr dt. And I know that the area of a circle is pi r squared, so I'm going to go ahead and write that over here. So I'm looking at what they give me. So they tell me that the radius is increasing at a rate of 2 feet per second. So that's going to be dr dt. And then the radius, or when the radius is 4 feet, so they're giving us that situation. So 4 feet. And then find the rate at which the area of the disturbed water is changing. So I'm solving for dA dt. Now, what I would tell you is I can find A, but if I look over here at my formula, I can see that when I take the derivative of this, A is going to be irrelevant because this A is just going to turn into dA dt. So if you want to find this, you can. Not going to be helpful. So a lot of times at this point, I'll just put a slash through that spot just to be like, hey, I don't need to find that, because otherwise you might end up going back and reading the problem and be like, did I need that? Like what was I solving for? So anyways, so dA dt then is equal to 2 pi r dr dt. And since I'm solving for dA dt, I can just go ahead and plug numbers in. It's already by itself. So this is 2 pi times 4 times 2. So that's what? 816 pi. Feet squared per second. Now, I can either leave it this way. Sometimes the book will leave them this way. Sometimes they'll multiply through. Really up to you how you want to leave it. but I'm not going to get like super picky about that. Obviously, if you needed to actually like legitimately solve for a value, you would have to find like the decimal number, but you know, like I said, up to you. A lot of times I end up just leaving it this way for that. Any questions about either of those ones so far? Okay. Whoops. All right, this next one, well, hopefully there's enough room. I'll just might not want to write huge on this one because there's a lot of little steps to this one that ends up happening. Yes. Yes. Are you here to take your quiz thing?
Yeah, what that was.
Yeah. Oh, yeah. Basically, what happened is the proof was really difficult and nobody got even half of it right.
Okay.
So I put an easier proof on the board and I let them do it, but it was after you left. So I have it. Let me.
So do I need to go get my book?
Yeah. Can you grab your Theory of Postulate book? Are you in study hall right now?
Yes, I am.
Do you want to just take this and do it in there and then bring it back?
Yeah, I can do that.
I trust you.
Yeah.
Just make sure you put your name on it since
I will.
it's not actually attached to your
Okay,
quiz.
thank you.
Yep. Okay. All right. So, anyways, yeah, just don't write huge on this one. This used to be one that they would say was a really good type question for the exam. So in the event that it comes back around and they decide to throw it on this one, this is a problem like this is kind of probably where I would hit, you know, focus, but I don't know. I'll keep tabs and see if they've like updated that they're going to put them back on this year as like a free response question, but I would think they would have already told us that. So anyways, so water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So, I'm going to start out with a little picture here of a tank. So I've got, it's crooked. Basically, an ice cream cone. Something like that. And they tell me that it has a radius of 5 feet. Now it says base radius, but obviously this is upside down, so that's really this value that's up here. So this is 5 feet. And then it says it has a height of 10 feet, so that's my total height here. Put this up here for a second. So that's 10 feet. And then it says, basically, I want to know what's happening when the water is 6 feet deep. So I've got this spot here. So a lot of times what you're going to find is, well, one, you need to know a lot of the volume and area formulas for different things like surface area, things like that. So the volume of a cone is 1/3 pi r squared h. And that kind of makes sense if you think about like a cylinder, right, of like a perfect cylinder, right, circular cylinder, whatever it's called. That formula is pi r squared, which is like the base of a circle, and then times the height for your volume. So essentially, if I take the cone out, there's 2 cones on the side, kind of, if you kind of like visualize it that way, like 3 triangles, and so that's where the 1/3 comes from for your cone. So if that helps to kind of remember it. So I like to go ahead and write this because then I know what variables I'm dealing with as far as like the side of it goes and all of that. So I'm going to go ahead and set this up over here. There's a few other things I need to draw, but I kind of need to see what I have, what I don't have to keep going. So I've got V, I've got R, I've got H, and then obviously dV dt, dr dt, and dH dt. So they didn't tell me volume, but I can look at the formula and know, just like with the last one with area, I'm not going to actually need volume, so I'm going to go ahead and just put a slash through that. I'm not going to need that. The base radius is basically 5 feet, so I'm going to put that there. The height is the height of the water. I would maybe put like a sub W or something like that, so you know it's for water. That's 6 feet. dV dt is, what is it? 9 cubic feet per minute. I was like, I could not find the number. So 9 feet cubed per minute. And I'm ultimately solving for the water level rising, which means I'm solving for dH dt. So one thing that's really helpful in solving problems like this are similar triangles. I don't know if you kind of remember those. I think it's like a geometry thing. We may have slightly done something with this at some point, but so if I take kind of like the right side of this cone and I look at it as if it's a right triangle, I can look at it basically like this, and then the water level is here, like the top of the water. And then this is the, obviously, you know, top of the tank here. This whole thing, thanks, is the height. Well, let me say this. The whole thing is 10. Let's do that. And then, let's see, what else do we have?
Top of the tank.
Oh yeah, thank you. This is 5. I'm gonna just put this up here. I was like, I know I have some other piece of information. What is it? So I'm going to try to essentially eliminate one of the variables. That's what similar triangles help me do. So I don't know what this radius is here. And I don't, well, it tells me, I guess, technically that the height of the water is, what, 6 feet? But I'm not going to actually use that. I'm going to be like, this is an unknown value, because that's something that's changing, is the height. Like, I will use that in the formula ultimately, but right now that's something that's changing. So if I do similar triangles, then I can solve for one of the variables and get it by itself. So I would have, basically, do it over here on the side, r over 5, so that's the two bases of these individual triangles. So I'm looking at the big triangle and then this little one at the bottom. I'd have r over 5 is equal to h over 10. And if I wanted to get, let's say, r by itself, then multiply by 5, so r equals 1/2 h. So then I can replace this in my formula, and now I can use this, and it'll just make my life a little bit easier as far as simplification goes. So my formula now is V equals 1/3 pi and then 1/2 h squared times h. So that ends up being basically 1/12 pi h cubed. Now I can take the derivative and just make my life a little bit easier as far as solving this. So dV dt is equal to 1/4 pi h squared dH dt. Ultimately, I'm solving for DHDT, so basically I'm going to be multiplying by 4, dividing by pi h squared. So, DHDT equals 4 times dV/dt over pi h squared. Plugging in numbers, 4 times 9 over pi times 6 squared. Just becomes 1 over pi, I think. 36, yeah. So 1 over pi feet per minute is the DHDT value then that I was solving for. So ultimately, because I did this, I really didn't need R. And part of the reason that I chose to solve for R over here is I knew I wasn't given dRdt. So I was like, well, if I'm not given dRdt, then I'm going to have to get rid of R because otherwise I can't do anything with that. But this is helpful a lot, even if we do have all the information. But sometimes we have to be careful because sometimes it can throw off the answer a little bit if, it shouldn't really do it. But since I didn't have it there, we had to use that. Questions on that one?
How did you know to look at the right triangle? Like when we took
Like
that
over here?
triangle? Yeah.
I could have used the left. It would be the exact same thing.
Well, I mean, just like.
Or are you saying just in general?
Yeah. Like I never would have thought to do that. I would have just been stuck.
Really, the only reason is because I've done them long enough to recognize it.
Oh, okay.
So it's one of those things where it's like I kind of just have to pass that knowledge on to you like it was passed on to me. Because, like, the initial thing is not going to be to do that. But if you have a cone or something like that, looking at similar triangles is going to be helpful. Because otherwise, like, looking at this, like, I would really have no idea how to, like, if I had R and dRdt, I wouldn't have necessarily done that. But because I was missing dRdt, I'm like, okay, I'm going to make, well, one, I have to get rid of R. But at the same time, I also have to recognize, like, or like it makes it easier to just have one variable in the problem than it does to have, like, 3 different variables in a problem. There's another one that we'll do, I think that's like a like sand pouring out of this like spout, and it basically makes the sand in like a cone shape. And I don't remember exactly what it's solving for, but I think we end up using similar triangles in that one as well to solve for it. I want to say there's one more at least that we'll use it, so we can kind of talk through it again with whatever one that ends up being as well. Let's see. We'll probably stop after this one. So we have a ladder is 25 feet long, leaning against the wall of the house. The base of the ladder is pulled away from the wall at the rate of 2 feet per second. You really hope you're not standing on it when that happens. How fast is the top ladder moving down the wall when the base is 7 feet? So I'm going to set up kind of a picture here of basically, a wall and the ground and then my ladder. Basically as a triangle. So my wall is going to be Y, the ground we'll call X, and then the ladder, if you want to stick with like Z, you can. Sometimes since it's like ladder, somebody will use L. Up to you how you want to do it. So I know how long the ladder is. I know that that's 25 feet. We're looking at basically how fast the ladder's moving when the base is 7 feet. So when it's 7 feet away from the thing, so this will be 7 here. So I'm gonna go ahead and set up x equals 7 feet. Y I'm gonna have to solve for. I'll just call it L for now. 25 feet for the ladder. Dx dt. They told me that it's being pulled away from the wall at 2 feet per second, so that's on the ground, so that's where that comes in as the dx dt. Dy dt. How fast is it moving down the wall? So that's going to be that value. By the fact that it's saying down the wall, I'm probably going to assume my answer is going to end up being negative, most likely. And then dz dt. Well, the ladder, we're not assuming it's one of those that you can change the height of. We're assuming it's a fixed ladder that's 25 feet. So that means that's not changing. So there's really nothing there as far as what that would be equal to. So first thing I'm going to need to do is I'm going to need to solve for y because, you know, right triangle, I'm assuming Pythagorean theorem. And so I know that I'm going to need to have y even once I take the derivative. So y equals the square root of 25 squared minus 7 squared. That's 24. It's Pythagorean triple. So then y is 24 feet. So now I'm trying to find dy dt. So take the derivative over here, and I'd get 2x dx dt plus 2y dy dt equals 2l, or z, whatever you're using, dl dt. Actually, looking at this, since we've said that the ladder is a constant thing and it's not changing, I can actually essentially, I don't know why I wrote dz dt over here. Essentially, I can either say, well, dl dt is 0 because it's not changing, so it's changing at 0, you know, feet per second. Or I can actually, up here in this formula, instead of writing this as L squared, I can actually go ahead and write this as 25 squared, meaning that that whole piece is going to go away when I take the derivative. So one way or the other, this is going to end up going to 0 over here. It just is a factor of when you want to do it. But if we know something's a constant value and can't be changing, then obviously you can just plug in the number straight up. So I'm solving for dy dt. So I'm going to subtract the 2x dx dt and then divide by 2y. So dy dt equals negative 2x dx dt over 2y. Well, I know that the 2's will cancel, and then I just need to plug in stuff at this point. So this is negative 7 times 2 divided by 24. So that's 14 over 24, or well, I can take out a 2. So negative 7 over 12, then, and then that'll be feet per second. So it's good to kind of, like how I pointed out, like, okay, this is probably going to be negative because it's moving down the wall, like that rate or whatever. It's good to kind of like think about that ahead of time, because if not, when you get a negative number, you might be like, oh, is this right or not? Like kind of thinking like, okay, is this number right? Because obviously when you solve for something, you want to think through, like, does this make sense as like a possible answer? Because if it doesn't make sense, then obviously, well, more than likely something has gone wrong. So at least I can recognize, like, okay, you know, I kind of expected that it could be a negative value, so I'm not surprised by the fact that that ends up being the case. So then consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So essentially, the hard part about these problems when it is a continuation like this is if you've gotten something wrong in the first part, you're going to end up using the wrong thing in the second part. But as I grade, if you use, because this happens a lot, if you use the wrong number, right, like you solved and you got the wrong number, and then you use the wrong number in the right way in the second part, I may take off like 1 or 2 points, but I'm not going to like double jeopardy you on like the whole thing because you missed something early on. So I'm going to go ahead and copy down the stuff that I had because now I need area as well. And then let's see, DADT. So area of a triangle is 1/2 base times height, but I don't have it as like B and H in this particular situation. I could have used those, but I had used X and Y. So 1/2 X times Y. Now, I can tell then from that formula, I'm not going to need A. I could find A if it asked me to actually find the area, but it's just asking me the rate of the area, or the rate that the area is changing. So I really only need to find DADT. So this is a product rule. So we've got DADT equals, I'm going to put the 1/2 with the X as far as like doing this. So this would be the derivative of the first would just be like 1 dx dt. So this is 1/2 y dx dt plus the first, so 1/2 x times the derivative of the second would be dy dt. And then now, because we're solving for dAdt, I just need to plug in over here. So I've got 1/2 times 24 times 2 plus 1/2 times 7 times -7/12. And then, let's see, 2's cancel there. So I have 24 plus, or minus 49/24. Anyways, this number ends up being 24 minus 9/24. 21.96 feet squared per second, since obviously area.
Could you go back to doing the derivative real quick?
Yeah.
Because I just got lost when you did the 1/2 y.
Oh, so I technically did the derivative of the first part. So the derivative of 1/2 x would be 1/2. Normally it would just be obviously 1/2. But because this is implicit, I have to do the dx dt.
So
So
you
I
just
just
put
put it at the end just
Oh,
because,
okay.
yeah. Normally whenever there's like a rate thing like that, we stick it at the end just
Okay.
more so for the look of it. But that was the only thing that I did. And then with the y one, obviously that one was in the right order. But yeah, technically speaking, the derivative of the first is 1/2 dx dt times the second y, plus the first 1/2 x times the derivative of the second, which is just dy dt. I'm okay also as far as like the area value. If you leave it here at like, I would say 2 decimal places is a good spot for that. And doing that way, if you put it as a fraction, that's also fine. A lot of times, obviously, we've been doing fractions on the other ones. If you were just so curious, as a fraction, this is 527 over 24. So, anyways, but that's that. So tomorrow we'll look at a few more out of this packet. My packet's all out of order up here. I'm definitely gonna do number 1 under the practice. The guy walking under a street lamp. That one will use like similar triangles as well. It'll make it easier to do that problem. And then we'll also, we might look at one more on that. I'm not sure. I'm gonna look and see where we're at and what I want to do with that. But there's a few in the book as well that we'll look at also, and then kind of what's left you'll have. So I would think that we definitely would finish it by Friday. You just may have problems to do next like Monday if there's a snow day potentially. But yeah, that's that.